Welcome to the deep dive. We know the drill, right? We take the topics you're really curious about, dive deep into the source material, and then we pull out the truly, the golden nuggets, the insights that matter.
Yeah, exactly. We like to think of this as that really efficient shortcut through some dense and sometimes complex information. You want to understand something, we're here to guide you, break it down, and really connect those dots.
So today we're tackling a really fascinating one, Euclidean geometry. You guys sent in a ton of great sources that explore kind of the historical roots in this field and the thinking behind Euclid's work.
Yeah, his really foundational work.
Totally foundational. And our mission today is to really paint a picture of how geometry went from, just kind of practical everyday stuff to a fully formalized system.
Right. And who are the key players? What are the core concepts, the building blocks? We want to give you a strong grasp of those basics.
So if you're ready to unlock the secrets of geometry, this is your express lane. All right, let's start with the basics. The word geometry itself, it's pretty revealing actually.
Oh, yeah, absolutely.
It comes from the Greek words geo, meaning earth, and metrain, meaning to measure.
And that right there, that tells you a lot about where this field started. I mean, think about it. Measuring land. Super practical, super essential.
Super essential. And our sources really highlight ancient Egypt as a prime example of this. I mean, every year the Nile would flood, right? And all boundaries, all those markers separating fields would just vanish.
Gone. Literally washed away. So they needed a way to reestablish those boundaries.
Exactly. They had to figure it out. And that's where you start to see the Egyptians developing these techniques, these rules that eventually formed the basis of geometry. They were calculating areas, figuring out constructions, even computing the volume of grain silos, which is so vital.
Right. Got to know how much food you can store. It's pretty important.
And don't forget the pyramids. Those incredible structures. They even had the formula for the volume of a truncated pyramid.
Yeah, that's next level stuff.
It shows a level of geometric understanding that was just really sophisticated for the time. This wasn't just problem solving, it was really laying the foundation for something much bigger.
Absolutely. When you step back and look at the bigger picture, it's clear that this practical need, this necessity, was a huge driver in the early development of geometry. And it wasn't just Egypt. The sources also talk about the Indus Valley civilization around 3000 BCE.
Oh, yeah, those incredibly well-planned cities like Harappa and Mohenjo-daro.
Parallel streets, amazing drainage systems. It just speaks to a really organized society.
Totally. And the fact that they had this standardized brick ratio length to breadth to thickness of 4.2.1 that just shows, the deliberate application of geometric principles. They were thinking about it. It wasn't random.
Yeah, exactly. And it wasn't just about aesthetics. It was about structure and functionality and safety.
And consistency. Like they weren't just winging it. They had a system.
Totally. So we see this practical geometry in action, this grasp of measurement and spatial relationships being put to use in these incredible ways. Then if we shift our focus a little bit further east, we come across ancient India and the Suba Sutras.
Oh, yes, dating back to about 800 to 500 BCE. And these were basically manuals for building.
Manuals, I think of them more like instruction sets, for constructing. And the thing is, they were all focused around these geometric constructions for religious rituals.
Right, the Vedic altars, the Vedas, and fireplaces, and the shape and area of those, whether they were square, circular for household rituals, or combinations of rectangles, triangles, trapeziums for public worship, it had to be precise. It wasn't just a suggestion.
Not a suggestion at all. They believed the accuracy was key to the whole effectiveness of the ritual. And it wasn't just, eyeballing it. The Suba Sutras gave very specific instructions on how to achieve that precision.
Right, like they had a real grasp on the how-to, on achieving these specific geometric results. But here's the thing. As our sources point out, a lot of these early civilizations, whether we're talking Egypt, Babylonia, India, even Rome, they were amazing at the practical applications of geometry, but they didn't really delve into the theory, into the why behind it all.
Right. It was very much a case of, it works, let's use it and move on.
Exactly. And that is where the Greeks come in. This is where we see a major shift in the approach to geometry. They were all about the reasoning, the proof, the underlying logic behind geometric truths.
Thales, a Greek mathematician who's often credited with the first known proof in geometry. I guess what he proved? That a circle is bisected by its diameter.
Something we kind of take for granted today, but he was the first to actually demonstrate why it's true. This was a game changer, moving from just knowing what worked to understanding why it worked.
It's a big moment in the history of thought, really, this emphasis on proof, on rigorous logical deduction. And that's a thread that continues with Thales' student, Pythagoras.
Ah, the Pythagorean theorem.
Exactly. He and his group really took things to the next level in terms of understanding geometric properties, developing theories, and that intellectual energy that focus on geometry continues for centuries until we get to the big one. Euclid, around 300 BCE.
The father of geometry, as some call him.
He wasn't just a mathematician, he was also a teacher in Alexandria, Egypt. And what he did was he took all this geometric knowledge that had been building up, and he organized it, he systematized it into his famous work, Elements.
13 books, a true masterpiece that shaped how we understand geometry even today. It's really the foundation, the bedrock of so much of mathematics.
And what's fascinating about Euclid's approach is how he envisioned geometry as this abstract model of the world, based on observations of space, of solid objects. He starts with solids, which exist in 3 dimensions, right? Then you got surfaces 2 dimensions, lines 1 dimension, and finally a point. No dimensions at all.
So he's essentially breaking it down, stripping away dimensions as he goes.
Exactly, like peeling back the layers of an onion.
So to build this model, Euclid starts with 23 definitions in Book 1 of Elements. And some of these are probably pretty familiar. Things like, a point is that which has no part, or a line is breadthless length and the ends of a line are points.
He also defines a straight line as a line which lies evenly with the points on itself. So it's not veering off or curving, it's consistent.
Consistent, right. A surface is defined as something which has length and breadth only, and the edges of a surface, well, those are lines. And then a plane surface is a surface that lies evenly with the straight lines on itself.
Okay, so we have these definitions, but as clear as they seem, when you really start to pick them apart, as our source encourages us to do, you run into a bit of a snag. Some of these definitions, they rely on you understanding other terms that themselves need defining.
It's like a circular definition trying to explain a word using that same word.
Yeah, so for example, a point having no part. Well, what's a part?
Right. If a part is something with area, then you have to define area, and on you go.
Infinite loop. So modern mathematicians, to avoid this whole infinite definition problem, they've kind of agreed to leave some basic terms, like point, line, and plane, if defined.
We get the idea intuitively, or we can represent them visually, even if it's not perfectly accurate. Like a dot on a piece of paper isn't truly dimensionless, but it gives us a way to think about a point.
It's a representation, a way to conceptualize it.
Exactly. So instead of relying solely on these potentially circular definitions, Euclid establishes what he calls assumptions. Things that are so self-evidently true that they don't need a proof. And he divides these into 2 categories, axioms and postulates.
Axioms are also known as common notions. These are truths that apply across mathematics, not just geometry.
Whereas postulates are specific to geometry. So let's look at some axioms. We have things which are equal to the same thing are equal to one another. This is like the foundation of logical deduction, right?
It allows us to connect equalities together. So if you have, for example, a triangle and a rectangle that have the same area, and that same rectangle has the same area as a particular square.
Then the triangle and the square must also have the same area.
Exactly. It's a fundamental principle. Then we have things like if equals are added to equals, the wholes are equal. And if you subtract equals from equals, the remainders are equal.
So basically just saying that if you perform the same operation on equal things, you get equal results. It's applying those basic algebraic ideas to geometric magnitudes.
Absolutely. And there's this one things which coincide with one another, are equal to one another.
This is like the basis for superposition, right? Imagining you can place one figure on top of another to see if they're identical.
Right, like a perfect match. And then there's the one that seems super obvious. The whole is greater than the part.
But the source points out that this is actually more like a definition of what greater than means. A greater than B means A is equal to B plus something else.
Right, it establishes that relationship. Then you have the axioms relating to doubling and halving. Things which are double of the same things are equal to one another, and things which are halves of the same things are equal to one another.
Just reinforcing that consistency with equality across different magnitudes. But importantly, and the source makes this point, Euclid specified that you can only compare and add magnitudes of the same kind.
Yeah, you can't compare a length to an area, right? Different dimensions, different beast altogether.
So now let's get into the postulates, 5 of them. The first one is, a straight line may be drawn from any one point to any other point. Seems pretty straightforward.
It does, but there's a hidden assumption in there that there's only one such line. Like today, we often state this as a separate axiom. Given 2 distinct points, there's exactly one line that passes through them. You can't draw 2 different straight lines connecting the same 2 points.
Makes sense. Postulate number 2, a terminated line can be produced indefinitely. So basically what we now call a line segment can be extended to make a full line.
Just keep going and going. Make it as long as you want. Postulate 3, a circle can be drawn with any center and any radius, a key tool for geometric constructions.
And postulate 4, all right angles are equal to one another. Seems obvious, but it establishes that standard for a right angle. It's a universal truth in Euclidean geometry.
Exactly. So right angles are right angles no matter where it is. And finally, we get to the fifth postulate, the famous one, and this one's a bit more of a mouthful. If a straight line falling on two straight lines makes the interior angles on the same side of it, taken together less than two right angles, then the two straight lines, if produced, indefinitely meet on that side on which the sum of angles is less than two right angles.
That's a lot to unpack.
It is. It is. So let's imagine you have two lines, AB and CD, and another line PQ, cutting across them both.
Okay, got it.
Now, if you look at the two interior angles on the same side of PQ, let's call them angle 1 and angle 2. If those two angles add up to less than 180 degrees, then if you extend AB and CD far enough on that same side, they will eventually intersect.
So essentially, if two lines are leaning towards each other and they go on forever, they'll eventually meet.
Exactly. Now, this one caused a lot of head-scratching over the centuries, because unlike the first four postulates, which seemed pretty self-evident to most people, the fifth postulate felt a lot less intuitive. And for centuries, mathematicians actually tried to prove it as a theorem derived from the other postulates.
They thought it was a consequence of the other rules, not a separate rule in itself.
Exactly. Now, it's interesting, the source points out that today the terms postulates and axioms are often used interchangeably. But the idea of a postulate has kind of evolved to mean a statement that's based on observation, and then it's tested or accepted as a starting point for a specific system.
And a consistent system of axioms is one where you can't derive any contradictions, like you can't prove something and then also prove its opposite.
That's key, consistency. That's how you build a reliable system of knowledge.
So Euclid, he had his definitions, axioms, and postulates, and then using deductive reasoning, he started proving statements. These are what we call propositions or theorems. And the source mentions that he managed to prove a whopping 465 propositions in Elements.
All built on that foundation he carefully laid out.
Pretty amazing. And the source gives us a couple of examples to illustrate this process. First one, if you have 3 points A, B, and C on a line with B in between A and C, then the length of AB plus the length of BC equals the length of AC.
Basic stuff, but it relies on Euclid's axiom 4, that things which coincide are equal, and the understanding that there's only one straight line through 2 points. So AB and BC together make up the whole line segment AC.
The second example is a construction. How to construct an equilateral triangle on a given line segment AB. You draw a circle with center A and radius AB, then another circle with center B and the same radius.
Where those circles intersect, let's call that point C. You connect A to C and B to C. You've got your triangle.
And to prove it's equilateral, you use postulate 3, allowing you to draw those circles, and axiom 1, things equal to the same thing are equal. AB is the radius of both circles, so AB equals AC and AB equals BC. Therefore, AC must equal BC. All sides are equal, equilateral triangle.
Nice and neat. But the source does point out that Euclid kind of assumed those circles would intersect without explicitly stating it.
An unstated assumption. Then there's theorem 5.1. Two distinct lines can't have more than 1 point in common, and this is proven by contradiction. Assume they do have 2 points in common, let's say P and Q.
But if two distinct lines go through both P and Q, that violates the axiom that there's only one unique line through 2 points. So the initial assumption must be wrong.
Two distinct lines can only intersect at 1 point, at most.
It's a classic example of how logic works within Euclid's system. And the source also mentions exercise 5.1, which has some true or false statements related to all this. Like, is it true that only one line can pass through a single point?
That one false. Infinitely many lines can.
Right. What about a terminated line can be produced indefinitely?
True, that's essentially postulate 2. And the exercise also talks about the importance of those initial definitions when you're trying to define other geometric terms. You can't define parallel lines or perpendicular lines, or even something simple like a square without first knowing what a line segment is, what a right angle is.
It shows how those more complex ideas build on those simpler concepts. And there are also some thought-provoking questions in there about what happens when you introduce new postulates and how you check if they mess things up within Euclid's system.
Really gets you thinking critically about those foundational elements.
Absolutely. So to wrap up this initial deep dive into the source material you shared, we've explored the core elements of Euclidean geometry, tracing it all the way back to those practical needs of ancient civilizations, like measuring land and building cities and even religious rituals.
Then we saw how the Greeks, with figures like Thales and Pythagoras, shifted towards this focus on deductive reasoning, on proving why things are true. And that led us to Euclid and his monumental work, Elements, where he brought it all together, creating a system that's still relevant today.
And while some of Euclid's definitions might seem a bit fuzzy by modern standards, his whole approach, starting with axioms and postulates and then building up from there, that was groundbreaking and incredibly influential. It really laid the foundation for how we think about mathematics, about logic in general.
And it's worth remembering that even something seemingly simple like the fifth postulate turned out to have some pretty profound implications, leading to the development of non-Euclidean geometries, which is a whole other fascinating story for another time.
It really makes you appreciate how those seemingly abstract concepts in math actually grew out of those very practical human needs and that innate curiosity we have about the world.
So here's something to think about as we sign off. This idea of starting with basic truths, axioms, and postulates, and then building up an entire system of knowledge. It's not just limited to geometry. It's everywhere. It's in science, it's in philosophy, it's even in our own personal beliefs. So what are your axioms? What are those fundamental truths that you base your understanding of the world on?
It's something to ponder, for sure.
It is, and on that note, we'll see you next time on The Deep Dive.
Until then.